Okay, so moving on to our second speaker of today, we are very happy to have Tevong, who will tell us about self-organized localization.
Okay, so thank you very much for the invitation to talk about this paper with Jan and Matthew. And we recently put out V3, which has some extended discussions on the measure problem, and there's a version that is now published. So we'll discuss a bit the measure problem at the end, which is the main maybe elephant in the room with regards to this approach. But the overall picture that I want to present is the general story of what we mean by self-organized localization. And the motivation is essentially to use criticality and quantum phase transitions as ways of understanding how problems in effective field theory expectations might be addressed by cosmology. The general mathematical framework for describing these solutions are the Fokker-Planck equation, in particular with the volume effect during inflation. And the new ingredient that we're adding to these dynamics, which are very well known already, is the effects of quantum phase transitions when solving for solutions of the Fokker-Planck equation. So these dynamics give rise to localization at critical points, and this is what we can apply to maybe understand problems such as metastability, the Higgs mass, and the cosmological constant. So the first part, I will skip through very quickly because I think we all understand the successes and problems of effective field theory. And in particular, the hierarchy problem is now also pointing towards the fact that we may need to look beyond typical symmetry-based solutions, given the lack of new physics at the TeV scale. But we already knew that the cosmological constant required some additional ingredients. So this is something that may point to new phenomena. The critical point that I want to make regarding critical points is that living at a critical point is really highly non-generic. Just like a fish living in a pond that is just about to freeze, but hasn't quite frozen yet, is something that might puzzle the fish living in such a pond. Why is it not living in a more generic liquid phase rather than being so close to transitioning to ice? This is something that we find in extrapolating within the standard model, the measurement of the top mass and the Higgs mass. And again, we seem to coincidentally live in this region of metastability that is on the boundary of two phases coexisting. So in our universe, we might be just as puzzled as the fish, assuming we are only living in a standard model universe. The other hint for near critical phenomena is the fact that the Higgs mass is again very close between two phases, just like the cosmological constant also seems to be very close to a boundary between two different phases. So all of these different hints are just that. They are hints that we don't have to take seriously, and conventional solutions might be, well, for the metastability, we just have new physics that restores the stability of the potential. For the Higgs mass, we expected some new dynamics, new symmetries to naturalize, in a sense, the Higgs sector. And for the cosmological constant, we had Weinberg's anthropic argument. But these things don't go all the way to explaining the problems that we want to address. For example, metastability might still be some accident that we want to actually have an explanation for, rather than saying this goes away with new physics. For the Higgs mass, as I mentioned before, the lack of new physics at the TeV scale suggests that maybe we are actually missing something. And the anthropic arguments for the CC don't go quite all the way towards explaining the value. So all of these motivate some potential new principle that we are missing. And what we want to argue is that self-organized criticality in the universe could actually play a role. This is not a new idea in the sense that it is known to explain how some emergent systems live close to their critical points through a kind of self-tuning process. And this was first pointed out by Backtang and Wiesenfeld in the famous sand pile model, where the critical slope of the sand pile self-tunes itself over time to always be at the value of the slope such that the size of the avalanches follows a pink noise distribution. So an ant living on a sand pile might question why the slope just happens to be the right size for the probabilities of avalanches to have this distribution. But from a more macroscopic perspective, this is essentially an interplay between the microscopic dynamics of sand grains and the macroscopic dynamics of gravity. And since then, this kind of self-tuning to live at a critical boundary has been found to describe many systems, which I've just shown here in a plot from Wikipedia, where all kinds of systems exhibit this kind of self-organized criticality. A recent theory which has gained acceptance is the idea that the brain is such a self-organized critical system where the sizes of the avalanches of neurons that trigger other neurons is not too ordered and not too chaotic, but happens to be at the boundary where things like epilepsy are due to going away from this kind of boundary. So we might want to take a more poetic point of view and take this quote from Victor Hugo as an inspiration for whether or not the creations of worlds or our universe might somehow be related to self-organized criticality in the same way as falling grains of sand. Concretely, this means that we need some kind of mechanism to realize self-organization in our universe. How are fundamental parameters self-organized to take their values that they do in our present universe? And this is something that has been explored in a very similar type of motivation by Justin Curry and collaborators in these papers, where they have a very different approach to ours, but with very similar spirit. In our case, what we want to use as a mechanism is cosmological fluctuations during inflation. These cosmological fluctuations, we find localized the scalar fields that fluctuate at the critical points. So what I mean by a quantum phase transition, just to clarify the terminology, is as opposed to a classical phase transition, which is triggered by lowering the temperature. And this is something that is very well understood and very well described in the history of our universe. What we want to explore is the idea of a phase transition that is triggered by varying a scalar field. So this background scalar field phi in this toy example is essentially scanning the potential of another scalar field psi. And through this term, you see that as phi goes from 0 to some non-zero value, it tilts the potential and at some critical point triggers the phase transition of the psi. And this psi scalar field, as it transitions from vacuum to another, will also have an effect on the phi field. So that's the general picture. Now, to quantify this in some more concrete way, we want to look at the dynamics of scalar fields during inflation, described through the famous framework of Starobinsky and Vilenkin and so on from the 80s, which is well known in stochastic dynamics to be described by a Langevin equation. The Langevin equation has a classical slow roll component from a slow rolling scalar field. And you can think of these stochastic terms as being drawn from a Gaussian, where the Hubble quantum fluctuations give some stochastic kick on top of these classical dynamics. The average of lots of these Langevin trajectories, which is a bit like a random walk on a classical potential, is then described by a volume averaged Langevin trajectory during inflation, and volume averaged because during inflation, one also has the effect of inflating at higher energy densities more than at lower energy densities. So this means that the usual Fokker-Planck equation, where the first term describes the quantum diffusion, the second term describes the classical drift, also has an additional term from the volume effect of inflation. This is also complicated by the fact that during inflation, in eternal inflation, one has an ambiguity in how one chooses the hypersurfaces. So the slicings in time is known as the measure problem, and I will come back to that at the end. But essentially, you can think of this as reparameterizing time through this one parameter family of possible time gauges, and this psi parameter can vary between 0 for proper time or 1 for scale factor gauge, for example. Sorry, the opposite, 0 for proper time for scale factor and 1 for proper time gauge. So we'll set psi to 1, and I'll come back to the dependence of the gauge at the end. It's important to realize as well that phi is not the inflaton. In this case, we assume inflation to be due to some other scalar field or some other background, which is approximately constant from the point of view of the phi dynamics. So this phi field that we call the aperon is restricted to, it doesn't have to be, but for the simplicity of the analysis, we can restrict phi to a perturbative field range where F is a typical field range that is within the effective field theory. This parameterization is convenient for analyzing the dynamics because we normalize the field to a dimensionless order 1 value, this fancy phi here. And the potential, we can expand around a local field value within the EFT range. And we can think of it as a monomial where we take, for simplicity, the linear first term. And this omega phi, you can think of as the potential that is a linear potential when we expand around the effective field theory value of the field. So we assume a subdominant energy density and expanding around the constant inflationary background rate H naught, where the contribution from the phi field is subdominant, we can write the Fokker-Planck volume equation in this form. So this alpha parameter parameterizes the quantum diffusion. It's essentially a dimensionless version of the Hubble scale of inflation. Beta is the ratio of F to M Planck squared, and this characterizes the size of the volume term and the typical field range F, which we'll see is usually super Planckian. In these units, the classical drift term is of order 1, and time is parameterized as the ratio to the relaxation time, TR. And it's clear why this is called the relaxation time, because parameterized in terms of alpha beta times this SDS quantity highlights the fact that the entropy bound SDS is the ratio of M Planck to Hubble, which is the maximum number of V-folds that is allowed for non-eternal inflation. Beyond that, one is necessarily in the eternal inflation regime. So the fact that the relaxation time, which is the time scale to explore the typical field range F for this kind of slope, can be written as alpha beta times SDS, means that when the dynamics are such that alpha times beta is greater than 1, the relaxation time is necessarily in the eternal inflation regime. And we'll see that when alpha beta is greater than 1, this is related to the behavior of quantum effects driving you up the potential. Okay, so as I said, the maximum number of V-folds is this SDS for non-eternal inflation. And we can see in a very generic way why the dynamics will be in the eternal inflation regime. The good thing about being in an eternal inflation regime, though, is that there is a lack of sensitivity to initial conditions. The solutions can be decomposed in terms of sum over stationary solutions, each with their own eigenvalues. And you see that the eigenvalues essentially characterize the inflation rate. So the stationary solution that is projected out at late times will be the one with the largest eigenvalue. And this means that no matter your initial condition and the sum over the solutions characterized by the initial condition, we are only interested in the largest eigenvalue projected out at late times. And so we can solve for the stationary distribution little p. Now, one way of seeing how without explicitly solving for a potential, we can see some features of this late time stationary solution. And the fact that this is a volume distribution means it must be positive. A physical solution must be positive across the entire field range. And one way to characterize the positivity of the solution is by looking locally at this equation and looking at it as a quadratic equation at that point. And the discriminant of that quadratic equation must be positive at all points in the field range, in particular at the boundaries, for that solution to be a physical stationary distribution at late times. Together with the fact that the eigenvalue determines the peak location, we can then take the maximum eigenvalue based on requiring, for example, that this discriminant be 0 at the boundary of the field range. So since phi is the order 1 field range in the effective field theory, then at the boundary at 1, if we required an absorbing boundary condition, then the discriminant must be 0 as a solution just passes through 0 at the boundary, and this tells us immediately what the maximum eigenvalue should be. And the peak location is then also determined by the Fokker-Planck volume equation. This gives a relation between the eigenvalue and the location of the peak. These are order 1 numbers. This is also an order 1 number. This is proportional to beta, so this dominates, and the location of the peak is determined by the eigenvalue. So plugging in that eigenvalue, this tells us where the peak should be, and we see that the peak wants to be as far to the right up the potential as possible if alpha beta is greater than 1 and this term is smaller. So this is also seen by just solving explicitly for a linear or quadratic potential. In this case, we can see for a linear potential the different solutions for different values of alpha beta. In what we call the classical regime, the solution for appropriate boundary conditions will be as far down the potential as possible. For alpha beta greater than 1, we see that it wants to be as far to the right as possible. And there's another regime where alpha squared beta is much greater than 1 because the peak is then closer to the edge of your field range by the size of the width of the peak. And so the solution now is one that is just about to oscillate to negative values and is bunched up at the, yep.
I have a confusion. Can you repeat what capital P is?
Capital P?
Yeah, in the previous slide. It gives the, yeah, capital P
Yes.
of phi and t. Physically means?
Capital P is the volume distribution. So this is the solution to the Fokker-Planck equation with the volume term.
Yeah, but yeah, so physically means?
So it's the volume, the size of the volume of your field phi that occupies the volume of your universe. The volume distribution.
Volume this.
The volume of how much of your field phi occupies the size of the universe. So if you take an initial condition where, for example, you have a delta function, initial condition of one field phi value, then you follow the Langevin trajectory of that field value. If you ignore the volume effects, then it's just a random walk. Then it's a probability distribution. It's normalized to 1, and it just tells you the probability of finding phi fluctuating here or there along the field range. So once you include the volume expansion effects, that when phi fluctuates up or down, then you also have the exponential volume expansion at every step. Then you average the volume expansion along one trajectory. Then that tells you the size of that volume starting from that delta function initial condition.
As the volume expands,
yep,
you create different pole patches, and those will have different value of the field.
Yes.
So which one are you tracking? I'm a little bit lost.
So that's why I say it's a volume average. If you imagine every possible trajectory,
yes,
where every time you jump from one, you're right, it expands, and then you have lots of other trajectories and so on.
Yes.
And you follow all of that up until some time.
Right.
Then you have a distribution of different volume sizes for different, you pick one path, it will have a different volume.
So for a fixed value of the field, it tells me how much volume, the probability that I get a certain volume for a certain
time.
Value of phi.
For a certain time, yes.
Yeah, I have to.
Okay.
Can you repeat? I can understand you better because you don't have a mass. So what's the interpretation?
So maybe the most intuitive way to see it is just following a single trajectory, okay, and ignoring the volume. Okay, then it's just a random walk with a gradient on a potential, right? But every time you fluctuate to one point, then inflation will inflate that Hubble patch, and then you have lots of other trajectories that will also have their own path. And you do this for lots of different time steps, then the average of the volume along each trajectory will give you, at some time slicing, a distribution of different sized volumes depending on the history of the trajectory. So essentially, it's not a normalized distribution, but it is something that gives you a probabilistic prediction by comparing the ratios of volumes for an equal time slicing. So when you look at the reheating surface, for example, if this was non-eternal inflation, then you have a finite reheating surface. It's a concrete calculation you can do to compare the volumes of different field values at the reheating surface. Okay. Because it determines what is the most likely value of phi that one would find at the reheating surface. This is the importance, essentially, of the reason why I'm talking about the peak location being determined by the eigenvalue, is that the peak location is the most likely value of phi.
So assuming you don't have eternal inflation, so you have a reheating surface.
Yep.
So what you want to compute is the probability
of,
that each value of phi has some volume.
Yes, exactly. Because the volume that dominates is the one that is the peak of P tells you that this phi value.
What is the most volume average? Yeah, likely value of phi if you have a reheating surface.
Exactly. Yeah.
Okay. Yeah, we computed this long ago, but we are getting a different equation. I'm not sure if they are compatible.
Different equation? Oh, you mean in the right?
We computed the volume.
Bacteria model for.
Huh?
Was this?
We exactly computed this probability distribution
yes.
of the volume at the end of inflation, right?
Yeah.
But I remember a different equation, so I'm a little bit confused. But maybe I don't know if they're compatible or not.
I thought they were the same equation. Wasn't it the Fokker-Planck equation with the volume effect?
And then you have to do some Laplace transforms to actually get the probability distribution. But okay, maybe this we can.
I think it's a different quantity. You computed the probability of having a certain volume for the universe or the multiverse, whatever you want to call it. With a particular value. What they're computing is the volume average probability of having a particular value of phi. So essentially, assume that you don't have eternal inflation. So you exit, you have a finite heating surface, so you can do the calculation finitely. Then you look how much volume a particular value of phi has. And then you do the probability distribution for that. Essentially, rather than doing a probability distribution, you do a volume weighted probability distribution. Essentially, assign a uniform prior to volume, and then you consider that as your probability distribution. That is essential, which is something different from what you do. You calculate the volume of the universe, right? I'm not calculating the.
But the volume of the universe is just one moment of the distribution.
Yeah,
compute a distribution for any value of phi, not just the total volume, which is, I think, is what we want to compute.
Sorry, which paper of yours are you referring to?
With the Senatore.
Right, the one with the bacteria model where you fluctuate along the.
The next, with the continuum limit of that, you get a differential equation, which is a modified Fokker-Planck. And yeah, then you have to do a Laplace transform. But okay.
Okay, I'll have to read it more carefully, and maybe you can discuss that after. Thanks. So yeah, the main point of this is to find the most likely value that the Fokker-Planck equation with volume effects will tell you determines the most probable value of phi, which then determines the most probable value of the parameter that it's scanning. And the essential aspect of this is that we want to be in the parameter space regime that is outlined here as a function of alpha and beta, because as I mentioned before, we want to first not have alpha be too small, since that would mean that the inflationary background field rate is no longer dominating. We also don't want to have beta be less than 1, because otherwise this is just a Fokker-Planck equation. There's no interest in volume effects. And we also don't want the quantum effect to be too strong or it just washes out any features, and we're not really interested in that. So the regimes that I'll talk about are the classical regime, the quantum times volume regime, and we'll see how these determine the features of the solutions that we'll use. The new aspect of including a quantum phase transition can be taken into account in this framework through the use of junction conditions. This is simply requiring continuity of the equation, since we know the solution has to be continuous across the discontinuities, which are induced by the phase transitions. And what I mean by that is if you look at this phi field, if it's scanning some other scalar field's potential, which then undergoes a phase transition at some critical value, as in the toy example that I mentioned earlier, then it starts with this other scalar field sitting at one vacuum before transitioning when phi goes beyond the critical point to another vacuum that then also affects phi's potential in this way. So we set the critical value to be at 0 without loss of generality, and you can see on the right the corresponding solution, which is the same solution that I showed before, take into account this junction condition across the discontinuity at the critical point. This is simply solving for the linear potential as before, but now requiring this to also be satisfied across the critical point. There is also another type of junction condition, which is if one looks at this phase transition more closely, then it doesn't happen in an instantaneous way, and one can have a supercooled phase or a phase where the transition hasn't quite completed across the critical point yet. And then the transition will happen at some transition point away from the critical point, as in this other example setup.
I have a very basic question.
Yep.
Is there another field direction than phi? What is the...
Yes, so sorry that I didn't do a two-dimensional plot, which would maybe make this clearer, but essentially the other direction coming out of the screen here is the, let's say, the psi scalar field. And
which is, what is psi? You've never mentioned psi before.
it's some other scalar field that it might be coupled to, for example, in this way.
So why aren't you writing an equation for psi as well?
Well, here it is.
No, for a Fokker.
Yes, okay, I'll get to the, so I'm just explaining here the effect of phi when it goes through a critical point. And then I'll show how this other scalar field could be like the Higgs, for example. And in this case, you also have a Fokker-Planck equation for that other scalar field. But that other scalar field doesn't have a super shallow potential, so you can essentially just take it to be sitting in its local minimum. So you're right that it will place constraints on this other scalar field that is coupled to, whether it's a psi or a Higgs or so on.
That depends on your scale of inflation.
Yes, exactly. It'll place constraints on the scale of inflation, because if then the scale of inflation is too high, for example, then psi can no longer be taken to be sitting at its minimum. And one has to then solve the two-field Fokker-Planck equation.
Exactly.
And
so why,
yes.
what in your scenario excludes this? What assumption that you have made so far excludes this scenario?
So the assumption is that psi is not affected by the Hubble fluctuations because the size of its potential is not as shallow as the phi potential.
No, but Hubble fluctuates during this entire period.
Yeah,
I
yes.
mean, assuming that you have this volume weight, why don't you fluctuate high enough so that psi starts fluctuating too?
Because Hubble isn't large enough for relative to the psi potential for psi to fluctuate significantly. But it is.
But it will fluctuate, right?
Yes.
Even if it's small, and then if you have a volume weighted measure, the moment you have a high enough Hubble, it will take over very quickly.
Yes, but it depends on the size of the psi potential, and if so for example, the Higgs sitting at its minimum, if Hubble is much, much smaller than that value, then you can take the Higgs to be sitting at its minimum without really being affected by
Yes,
those
but I
fluctuations.
don't understand how this is. You haven't shown that this is a good assumption, given that Hubble jumps during this entire time.
So we have concrete numbers where you can show that for a range of Hubble values, which I'll come to later, this will restrict the parameter space for Hubble being smaller than a certain value for this assumption to be valid.
But you also have a regime which also shown that you have internal inflation, essentially.
Yes.
So there, why doesn't Hubble change during that time?
Well, let me put it this way. If you take the stationary distribution, okay, then the stationary distribution for your field, when you solve this equation, okay, will give you a peak somewhere, okay?
I mean,
Now,
the moment you have quantum inflation, you just jump around randomly. So
no, this is exactly
no,
what
just
the
fine.
resulting
You're
asymptotic stationary distribution
you're
will do.
ignoring inflationary fluctuations. You're ignoring psi fluctuations.
No, we're not ignoring the fluctuations. This is precisely what's being calculated here.
You're calculating only the fluctuations in that one field while you have three scalar
Right.
fields in your theory.
So the Hubble fluctuations for the phi field are being calculated here. You can
Yeah,
do
but there is the inflaton itself.
yes, you can do the calculation for any other field during inflation as well. Okay,
So you need to do all three at the same time, especially if you're in the quantum regime where you have lost control.
Can be bound, right?
Why can't it be bound? You say what it is. I don't understand this entire formulation without stating what all three scalars do at the same time.
So you can solve the Fokker-Planck equation for two field dynamics at the same time. If both of the fields are very light, then yes, the fluctuations have to be solved together in a coupled way. If one field is very heavy, then you can do it in a coupled way, but you'll find that take a quadratic potential for a field and then the asymptotic stationary distribution, no matter what happens, is just going to sit at its minimum.
Can I maybe clarify, try to clarify the question? Is the question the following? So if you look at the inflaton potential, you should be able to jump way up that potential, and then Hubble is large. Is that what you're asking?
You have three scalar field directions. Each one of these directions can jump. And I'm not even commenting on the starting point. You have a regime, you say you have quantum, you have eternal inflation essentially. So when you have eternal inflation, everything that can happen will happen. And you
Yes,
have a
right.
volume weighted measure. So a random fluctuation of any one of these three that goes to a Hubble close to the cutoff will dominate the dynamics.
Yes, and this is precisely what's being calculated.
I don't understand. Calculating one phi field fluctuation for one specific Hubble.
Because H0 is on such a different scale that you can take the Fokker-Planck equation for the two field distribution and they'll just factorize.
No, but this
in
is,
two
you
ways.
don't, yes, the inflaton itself will fluctuate. H0 will jump around.
You just have to say that the inflaton is just
You don't say, you calculate. You don't understand the statement.
No. I'm saying
You need math. You have eternal inflation that has infinities.
no, but I'm saying
Okay.
And you're using words.
Let me put it, okay, here's maybe one thing that you can do. You can keep the field dependence in Hubble, okay? You don't have to do this expansion. You don't have to assume a constant H0, okay? But what you can show is that the phi dependence, for example, of Hubble is subdominant. What you can show is just plug it in, H phi in there, and then look at the terms where you have the phi dependence in there, and they're subdominant in the slow roll regime where phi is slow rolling. So you can ignore the phi dependence of phi fluctuating on the Hubble rate in these terms, okay?
Mina, I think that the Black reaction is taken into account precisely because of the volume term. And this is the reason why in certain regime, the distribution is picked on the right. To show again the distribution picked on the right, it's telling you exactly that. The top inflates more.
She asked about the inflaton. She asked about the inflaton. Yeah.
So this calculation applied to the inflaton is precisely what tells you that the inflaton will be eternally inflating. You do
No,
this.
but the question is the following. I think let me try to understand it myself. So she's saying the following. You assume that the other field is classical, right? While that is true for a small Hubble, whereas if you have in your theory a high inflaton phase where it has a much larger Hubble, it will eventually go there, and because the inflation is eternal, it will always be the one that's dominating. So I think you have to say that your inflaton is a very specific model where it's bounded from above in terms of the potential. It cannot go arbitrarily high in terms of the value, because is that correct?
I think that there is
So, for instance, an axion like
right,
inflaton, where it would have a maximum, but then you have to ask why the inflaton is not at the maximum. But maybe it's a different question. But then maybe you don't have that problem. Is that correct?
Yeah, but I don't understand. Again, you need to take everything. You want to argue about what happens. He's on the mic.
But that's
The moment that, I mean, the moment you have eternal inflation, everything that can happen will happen. So you have to make sure that you keep, yeah, I mean, it's.
You have to make a UV statement about what the inflaton
Exactly.
Okay,
Well, no, you need to control the theory everywhere, because if you shouldn't have, yeah. So I don't know that.
okay.
Shown that.
You're okay. If you're thinking of the inflaton, for one, the inflaton on a potential will also have a stationary distribution. Okay, it's not just going to go up and up and up and up and forever. It will reach a steady state configuration as well. Okay, so that's.
But your eternal inflation, so that means.
In eternal inflation, I'm talking.
It will be climbing up that potential as well.
Yes,
they
yes,
have a boundary condition.
but it'll
right,
reach a steady state configuration, just like any other field during. I mean,
But that will change whatever Hubble you assume. You need to decouple all
Yes,
the
okay,
dynamics. You
that's-
cannot just decouple everything. That's
yes, but the point.
now you're keeping Hubble fixed, and you're doing small fluctuation of Hubble around that point.
The point is the Hubble value, okay, can be treated essentially as a constant background, because from the
But
point of view
that's-
of the phi field, the variation in this Hubble.
That's
not-
not precisely my point. You have eternal inflation. You cannot do that. You're
Okay.
making statements about the regime where you have no longer control.
What about take an old inflation type model where it's just sitting in a
I
in a
don't know. You
metastable
tell me.
vacuum,
You have
okay?
to put down equations. I don't know what that means. All deflation. You have eternal inflation. Jumping up or down will happen, and it will happen infinite times.
Okay, take essentially this potential, okay, where it's sitting at its potential, and inflation ends when it tunnels through and then reaches reheating and then tunnels. This is an eternal inflation model. Okay, the value of Hubble when it's sitting here is just the value of Hubble where inflation happens. It's eternally inflating because the tunneling probability
You
is.
can jump to the top. There are so many things.
Okay, now you're saying you can jump to the top, okay, but this difference is not going to matter from the point of view of the dynamics of
But you
a phi
have
field.
other fields in the theory. You have 3 scalar field directions, and you haven't shown that there are not other vacua close to the cutoff that you cannot jump to and will dominate the energy density. I don't understand effective field theory prescription that you're using, given that you have honest to God true infinities. I don't think this has percolated.
So I don't see what the fact that we are in eternal inflation and there are infinities has to do with the fact that this is an eternal inflation model where inflation is eternal. The Hubble value of that eternal inflation model is maybe not constant from the point of view of if you solve for the Fokker-Planck dynamics of this, you'll just sit here with some probability to fluctuate upwards. But the other direction is not going to be affected by whether it's sitting here or there or there. It's going to vary by some amount, but it's not going to significantly change the fact that this large Hubble value as a background value is going to cause this other direction to fluctuate.
I
It
think
might cause it to fluctuate a bit more if it's sitting up here than if it's sitting
Let's
there.
Please continue, because I don't think I'm communicating my point very well.
So the only important thing from the point of view of this other direction is that there is something causing it to fluctuate. That something, you're right, will vary and will have its own Fokker-Planck dynamics that causes it to vary. But from the point of view of this other direction, it is more or less of the size of h naught. And it is, whether it's more or less, doesn't really affect the fact that this other direction is going to get a kick of an approximately h naught size. And this is eternal, but it doesn't mean that anything that can happen is going to happen within an order h naught. It's not.
Tevong, let's maybe continue and discuss this point afterwards.
Okay.
Yeah.
So this is the solution, which is the asymptotically stationary solution when one includes the phase transitions across a critical point. The asymptotically stationary distribution that we see here will be peaked at the critical value. So this is the volume that will dominate essentially. If we have a finite reheating surface, then this is unambiguously the value of phi that dominates the volume at that reheating surface. So this other direction, psi, in which we have this vacuum phase transition that realizes the critical point, can also be something that happens at a transition point once one goes beyond that critical point. Once one goes beyond that critical point, then the phase transition completes essentially at this transition point. And this leads to a flux conservation condition that, again, if one solves the Fokker-Planck equation, take into account the flux conservation conditions, the peak of the distribution along this phase will be at the critical point, as we show with an explicit solution here, which from the point of view of this phase is not a special point of the potential. As I mentioned before, if this was in the classical phase, one could expect the solution to go all the way down, but depending on the boundary condition, the solution could also be peaked anywhere along this potential, but it is through the transition and the connection with the hidden phase that the energy densities of the two phases are degenerate at the critical point, and this is where the solution will want to be peaked. I'll come back to this solution for the cosmological constant solution. This is something that I can go into in a bit more detail after. The important point is that on this phase V, the solution must be in the classical regime, because in the quantum regime, the solution will want to go as far up as possible. In the classical regime, the solution will want to go as far down as possible, assuming absorbing boundary conditions. But if one has a non-zero flux at the boundary, then the solution can be peaked anywhere along this, depending on the maximum eigenvalue. And it is precisely through the equilibrium with this hidden phase that the eigenvalue at which it is peaked will be at the critical point. So this is where the role of the boundary conditions and the fact that the V phase must be in the classical regime will be important. Okay, so I'll quickly just go through the possible applications of such a localized solution at critical points through three separate examples. These are not to be taken as simultaneous solutions. The first is to address the Higgs metastability. One couples phi to the quartic. The quartic of the Higgs potential is being scanned by this phi field. And we, again, just shifted coordinates such that the critical point will be at 0. So when phi is negative, the quartic is positive. And in this IR phase, the Higgs will be sitting at its minimum. So this Higgs will have its own Fokker-Planck dynamics, but it will essentially still be localized at its minimum. as phi starts evolving beyond the critical point, then the quartic turns negative, but we have this phase where the Higgs hasn't quite transitioned yet, up until some point where it will definitely transition, because at that point, there will be no minimum in the IR left. And in this case, we are left with this UV phase, and this is the phi potential at that point. So this is where the dynamics of the Higgs potential can be relevant. So let me just show this plot rather than the other one, because I think it's more intuitive to show on the parameter space of Hubble versus the cutoff of the theory M, given that the metastability values that are measured for the Higgs and the top mass tell us that we should be living within this region. This grayed out region here is where Hubble fluctuations are too large. If the Hubble fluctuations are too large, then the Higgs can no longer be taken to be sitting at its minimum, and this is what excludes all this parameter space at the bottom. All the parameter space at the top here is excluded by the fact that the inflationary rate will then no longer be set by the inflaton, and the energy density will no longer be subdominant. So this is the parameter space within which the self-organized localization minimum might explain the coincidence of living near metastability. The other application is to, yep. Yep.
So so you chose a specific initial condition for phi, and then you time evolved it?
Yes, so we do that, but it's not important for the eternal inflation regime because we just want the stationary solution at late times. But you can, and we did, start with a delta function initial condition or some Gaussian initial condition. And you can see the time evolving solution reach the stationary distribution over time. Yes.
Yeah, yeah, I was going to ask, in fact, for how sensitive you are to the initial conditions that you assume for phi.
This is one of the benefits of being in eternal inflation in that you aren't sensitive at all to the initial condition because it contains a range of eigenvalues of which only the largest will be projected out at late times. So no matter what your initial condition is, it'll contain the asymptotically stationary solution. So in that sense, it doesn't matter if you start with a delta function initial condition, if you start with a Gaussian, if you start with something that is even more delocalized or localized, or where it is. At the end, you'll always project out the largest eigenvalue, and that is the stationary solution that determines the peak at the critical point. Why am I sorry? Oh, exactly because of what you mentioned, that if the Hubble fluctuations are too large, then it'll destabilize the Higgs. And then you're right, you do have to solve the two-field Fokker-Planck equation.
Yeah, so then why are we not in that space or the place where rho phi dominates over the inflaton?
Because there is no Hubble that will go larger than that.
I don't understand what that means. Your theory can do it clearly and you lose control of it. So the only reason you are excluding this region is because you think
these parameters are fixed, right? As
what
in
parameters are fixed?
As in the cutoff of your theory, big M, the Hubble weight, yes, you're right. If the Hubble weight is in this gray region, then the Hubble fluctuations will destabilize the Higgs. So this is the maximum Hubble weight that if there was some way for the Hubble weight to be larger than this top of the potential, then it would be excluded. But the Hubble weight is fixed essentially by what the inflaton potential is.
Which you don't say.
No, because from the point of view of.
But the energy density is a dependence on all the positions of all the fields.
Yes, but there is a maximum, right? You can write down the potential. You can look at the size of the potential and in the landscape or whatever.
Cutoff.
Sorry?
That maximum is the cutoff of the theory.
Yes.
So I don't.
And that can give you a Hubble rate that is bounded. And as long as that bounded Hubble rate is not larger than a certain value, then it doesn't matter what the inflaton is doing. You'll never be in this gray region.
So maybe I can say this in another way. You're basically, you cannot think of a generic landscape. There is a UV sensitivity in the sense that you cannot continue, for instance, this inflaton potential on the left where it would reach much higher values.
Right.
You have to say that, and there's no place in the landscape where that happens, because if there is a place in the landscape where that happens, that's what's going to dominate your Fokker-Planck.
Right. So, yeah, I should say more explicitly then that the inflaton potential, if you just write it down and you look at the inflaton potential in this landscape, this is what I mean by the Hubble rate will not be larger than a certain value. And to the extent that it does fluctuate, as long as it, yeah, okay. So I see you're saying, okay, what if in that landscape you have Hubble values that are huge, then it'll fluctuate, it'll go up to there, right? But what I'm saying is that this landscape, you can write down the potential, you can look at what is the maximum Hubble as you fluctuate around this. As long as that doesn't go above a certain value, then it doesn't have. Right. So the specification of that was essentially to say that H0 is assumed to be constant. That's what the hidden assumption is behind this H0 being constant. But it's one that's done just for simplicity of calculation. I mean, you can do the full two-field equation. There's nothing stopping you from doing that. Three fields, yes, if you want.
You need to know what your, yeah, his battery is out. So no, but you need to know exactly. That's precisely the point. You need to know every point in your UV theory and exactly what it does to make predictions.
But you know, you could do this three field. Okay, you have your inflaton. Well,
but our theory, we know the standard
direction.
we need more degrees of freedom. We know we need UV completion of quantum gravity. You know, have string theory. You know, this is a toy of a landscape.
No, it's a valid approximation in certain UV completions where you can neglect the Hubble fluctuations of the other fields. If you had to solve every time for every scalar field that exists in our universe, you would never be able to understand anything. The fact
But
is,
that's
there
the
are
point
regimes
about the multiverse. Do you now you understand that's precisely the point. The string landscape has 10 to the 500 vacua created by hundreds of scalar fields. In order to keep track of everything that's happening in that landscape, you need to keep track of all those fields if you want to do the type of analysis you're doing.
Otherwise, you wouldn't be able to even understand how the Higgs fluctuates during inflation. If
But
you were to, but let's say that you have the dynamics of an axion. An axion just slow rolling along its potential. It reaches some wiggles and it gets
But
stopped
that's
there.
precisely the point, that there is no
to...
problem with the misalignment mechanism. Inflation does have, if you ask Andre Linde, inflation itself, he claims inflation is a landscape. It does have an anthropic component. In the case of inflation, prediction of iron spectrum. In order to do the exercise, also wanted to do is explain the initial condition. You have flat. Here, you want to make arguments about where you end up. If you want to make arguments about where you end up, to solve external inflation system of all the degrees of freedom that your theory has, effectively doesn't work in the way you write it. This is the measure
you can
problem. This is the measure problem. People
You can always look. You can always look at one field
no,
along one patch of a potential.
no, you cannot. That's precisely the statement of the measure problem. Do that. People that wrote down Busso, Lenny, Polchinski,
Okay.
they thought about these issues and they
what I agree on completely is yes, the important thing about the final distribution, where we have a stationary value of the maximum allowed value of phi and it has a certain distribution, yes, you have to project that onto the reheating surface. In that sense, the dynamics of the inflaton and in association every other scalar field, which might affect those dynamics, will be important. And the solution to the measure problem will affect the final form of the distribution when you try to predict the values of these phis. But it is not to say that it isn't something that you can calculate, as in.
I don't know what. Through infinities, problems with the volume weighted measure.
Yes.
There are problems with the entropy measure.
Right.
There's Boltzmann brains, there's Young's paradox, there's all sorts of things that people came up with.
Yes, and this is all discussed in our paper. So this is not to say that you can't make predictions if you take a solution to the measure problem. Okay.
The strong couple theory, I'm going to guess, I don't know.
No.
The solution and then make predictions.
So the measure problem doesn't mean you can't make predictions. You just have to assume a solution to the measure problem. Take a solution to the measure problem.
Do you understand that this is
right?
There that we are not necessarily connected with.
Yes, because we don't yet have a accepted solution to the measure problem.
What do you mean accepted? It's going to be decided by consensus. A theory that has a UV, like string theory, should have a unique prediction. It's like, I'm telling you again,
Yes,
it's like trying to guess what the solution to QCD is without having the tools to even calculate.
No, it's like saying that we don't know renormalization yet, but because there are infinities in QFT, we should just abandon trying to do any calculations in QFT.
No, but QFT, there was a way to test. Here, I don't even know not the same type of infinities.
Right, but it is an infinity that in some solution to the measure problem, one day if we discover an unambiguous solution to how to make sense of these infinities.
Try. It's why is this? Did you spend time just choice?
This is what I was going to get to in the last slide, to basically discuss how the measure problem affects the result of this volume distribution. Because in some solutions to the measure problem, you can actually have the same solution with the same peaks and the same features in some ways to make sense of infinities and Isothermal inflation. But it depends on whether or not you accept that as a sensible solution to the measure problem or not. And we don't know yet that solution.
Tevong, let's maybe move on. How much time do you need to finish?
So just 2 more slides.
Okay.
So this is essentially the other application would be by coupling the phi to the quadratic of the Higgs potential, one can essentially localize phi at the point at which we have a natural Higgs mass. The model building in this case is a bit more involved because the prediction would then be that the weak scale would be at the instability scale at which the phase transition happens, which in the standard model we know is much too high. So
here, for example, why are you keeping the gauge coupling fixed? Why are you not considering things that change the quartic of the Higgs as well? I mean,
So-
there are all sorts of things that will happen. Even the particle spectrum will not be the same.
It
Even
could
the
be, but we're
even the
talking about a different
dimensionality
model.
of space. No, it's not a different model. It's the string landscape. In many vacuum of 10,500, we don't even have 4 dimensions. It's not 3+1.
Yes.
Exactly, precisely. So I don't understand, but that's precisely the point. Without knowing what UV completion is and know the entire vacuum structure, how can you make statements a toy of a toy?
One statement you can make is that for this to work, it puts a very strong constraint on it. Whether there exists a UV theory that made these constraints,
I don't understand.
This means 100 scalar fields, each one in 10 different states.
Yeah, I mean, you could have phi coupling also to the quartic, and then you'd have to look at that solution together with the quartic. These are just the simplest possible examples. Take them as toys. Take them as something that just demonstrates in a very simple calculable setting how this can arise. And then you can look at more complicated dynamics. You can couple it simultaneously with 3 fields, 2 fields, and allow everything to vary simultaneously. So the point is the dynamics, if one only couples to the quadratic and takes, for example, the following vacuum structure, then the prediction is for the instability scale to be to set the vacuum expectation value of the Higgs, but we need to lower that instability scale to then also have the weak scale be what it is, which requires the addition of vector-like fermions at the TeV scale to reduce that instability. So I can come back to more explanations of this kind of setup, but the final example that I want to mention is the Higgs mass, that is the cosmological constant solution. So for the cosmological constant solution, this is the other junction condition that I mentioned for this kind of setup, where if one were to just look at the visible phase, then someone living on this type of potential would be puzzled as to why the peak would necessarily be localized at this particular value when the other value is good. But the degeneracy of the vacuum at the location of this critical point is what sets the maximum expansion rate in equilibrium. So the stationary distribution that one would find in the visible phase essentially has some kind of equilibrium with the hidden phase, which localizes the peak at this point. So yeah, sorry, I didn't mention that.
What are the axes?
So on this hidden phase, one has a supersymmetry and an R-symmetry that sets the cosmological constant to vanish. So this hidden phase is protected by supersymmetry to have a vanishing CC. So this is a hidden phase that is protected with a supersymmetry, and it is sequestered. No, this is not our phase. This is not the visible sector.
No, it
does through Planck suppressed operators, yes.
But it's a phase, it's a different phase where the standard model is supersymmetric, right? Is that correct?
Yes, so yes, but it's a different phase. This isn't our vacuum. We live in this vacuum, the visible phase, where supersymmetry is broken. But the point is that the maximum of the volume distribution will be peaked at this point because during eternal inflation, it essentially comes to an equilibrium with this hidden phase. It means if you solve the Fokker-Planck volume equation in this kind of setup, as I showed before, the peak of where phi that sets the CC in our current universe localizes itself to be at the value of the CC that we observe these days. This is the potential in our universe, this phase V, and where phi is localized determines.
Higgs, I don't understand. There is another direction of the Higgs, and if you have supersymmetry, there is other scalar direction. So I don't understand what the lines you're drawing even mean.
Okay, so this is, yes, there are lots of other directions, but you can take them as other fields doing their own thing, which will localize in their own way. So when you solve for this phi direction, you also solve for other directions, and they will also localize in their own. So the volume distribution won't be something that you can plot.
So what is the mass of this guy? What is the mass of the other guys? What is Hubble inflation here? I mean, you need to say what are these parameters?
Yes, I mean, they're, okay, so.
What? Oh, the other one. Oh.
It's another Zoom, and it's another topic. So I'm going to, or yeah, not too much.
Can you say more about how the field couples to gravity? How does it couple to cosmological constant? Can you write the Lagrangian?
Our assumption is that there are just these two phases. There will be complications from having other scalar fields. Okay.
What is the, can you write something concrete down? Can you write a Lagrangian of how it couples to the cosmological constant and the Higgs and us and everything?
This is just a toy example, okay? I'm not trying to say that if you don't have a full landscape with lots of other scalars, then this solution will be the solution, okay?
But what protects, our sector has a problem. If you had supersymmetry at a millimeter, there wouldn't be a cosmological constant problem. So, yes. So I'm asking what is the scale of supersymmetry for this sector, and it will be broken through gravity because it couples to just through gravity-mediated SUSY breaking.
Yeah, so in our vacuum, we live in a broken supersymmetric phase. Okay, now in our vacuum, in our broken supersymmetric vacuum, let's just say that phi, which is some scalar field that can determine the CC in our vacuum by being put at different locations. I can put it by hand to be here and just say that our CC is the value it is because I put phi by hand to be that value. Now, what if phi is there because at some earlier time, it was localized to be there and hasn't evolved significantly since, because the potential is so flat that once it was fixed to be there at earlier times, it essentially is still there now.
It will be there now because the mass of that field will get millimeter gravitational induced correction. So the natural value for phi is that it has started oscillating way before BBN. So the value that you predicted after you reheat it has changed dramatically. So I don't even know.
Yeah, so this is why the potential is super, super flat. And F is super duper Planckian.
It's not protected by, you couple to astrogravity. Why doesn't gravity generate a mass for phi?
Okay, so you're asking for a UV completion that justifies a super flat potential.
Of course.
Yes.
But
okay.
Potentially, this hoopla.
Is the top. That is where that intersection is where the field will be localized. And the importance of that localized, if this was just some other phase, it would just be localized there, you're right, there would be no importance. But if this hidden phase has a vacuum energy with a 0 cosmological constant because it's protected by a symmetry, then in a sense, our phase knows about that through the fact that it came to rest at this point in an earlier phase. It just means that, right. Yes, so in that phase, the top, all of that is true, okay? In that phase. In the visible phase where all of this is broken. No, because no, because this is on our visible phase, supersymmetry could be broken and broken at a high scale, and the superpartners be very heavy, and we'll never measure them. So no, because phi, which sets the vacuum energy, is low. So no, here it's not the same model as the one in the previous one. Because it knows about Susie not through the fact that in this visible phase it is supersymmetric and so on. It is simply the phi doesn't couple to the phi is not related to the Higgs, or it doesn't set the Higgs in this example, or it doesn't. It's simply an evolving. It doesn't couple to the standard model in a way that affects its potential. That's the only constraint, that the potential has to be very super duper flat, and it's just a scalar field that fluctuates, and that's it. You can think that's the point. It's just the fact that it localizes at the point at which the CC is 0. Oh yes, on the hidden phase, it affects the transition, which then creates the. Yes. Yeah. Yes, the boundary condition that I mentioned before, and the fact that it's in the classical regime, is what picks out the solution that localizes it there. But yeah, so that's the UV completion that is important for. But I think that's a different aspect to the construction of these solutions than than what Savas was asking about. But yeah. So yes, you're after. Yeah. So the cosmological history is essentially the fact that it localizes with a constant uplift of the vacuum energy from the inflaton. Okay. And then after inflation and reheating, it doesn't move far away from where it's localized. So the CC that was fixed during inflation, after reheating and going through the electroweak phase transition and QCD phase transition, is still yeah. I mean, you could also have other scalars that also have their own vacuum expectation value that would mess this up and so on. I mean, these are all possibilities in the landscape that one could complicate the story, but yes. Yeah, I mean, in 35 minutes, I can't explain all the assumptions in the parameter space and the values and so on. Yeah. No, I mean, this is it basically. This is the only overview that I wanted to give. Essentially was an introduction with toy models and a sketch of the general ideas, where you're right, I apologize for not going into more specifics about the scales and the values and the numbers involved, which can be actually pretty scary when you look at how flat the potential has to be within the dark energy equation of state constraints and so on. Means this is not necessarily a generic occurrence in terms of having such a super flat potential and how to justify it in UV completions. The only message that I want to emphasize is the localization of a scalar field that is fluctuating at a critical point is something that comes out of the equations describing fluctuating scalar fields. Now, their application to these solutions are indicative that they might be responsible for explaining the fundamental parameters. And within a more UV complete setup, one would then have to justify essentially the things beyond the EFT field range of the local potential that we're considering. So things like the flux at the boundary for the classical solution, things like the effects of other scalar fields, what is the inflaton sector, how do you solve the measure problem? So one of the things that we did expand on in the published version was precisely how the measure problem might affect this solution. So we show two examples of how concretely, if you choose two solutions to the measure problem that have been proposed, exponential localization can remain a feature. Do we believe that these two solutions that we looked at are the solution to the measure problem? No. But if we one day understand this in a more satisfying way, and there is progress in that direction, we're hopeful that this could still give something like an exponential localization. And this depends on this psi parameter, which parameterizes this uncertainty in a crucial way. So thanks for this nice discussion. And I'm happy to discuss further as well, more specifically.
Maybe we can release the audience who don't want to stay for this discussion. You're welcome to go, and we can continue this discussion here.
Yep.
Sounds good.
Yeah.
There is more than one choice. It's not just that you are parameterizing choosing a measure.
You're choosing a what, sorry?
A volume weighted measure.
Yeah, exactly.
That's a very specific choice.
Yeah, I mean, this Disk C is one way of seeing how the volume weighted measure depends on that choice of slicing. Yeah.
Yeah, but the point is that there are different measures, and all of them have different people weighted measure, and they reject it. It had its problems. So the other thing is choosing a finite range of field and putting random boundary conditions at the boundary of that range is not clear what you learn from that exercise. See, the problem, my frustration is the following, because there appear to be equations. You have some control of what is happening. In reality, there is no such control because precisely of the issue at hand, the landscape inherently has eternal inflation. These are honest to God true infinities. Whatever happens, yeah, you think it's funny. I don't know. Are you laughing? Okay. So the point is that if whatever happens will happen, whatever can happen will happen, and will happen for an infinite amount of times. And you have no control over it. There are Young's paradoxes, all sorts of weird things that people have come up with different measures. And this is starting with basic point.
No, but the point is that the fact that there are things like the Young's paradox and the measure problem and the existence of a string landscape in which we realistically expect all kinds of other things as well as these does not mean that we can't look at a simplified setting where we can try to understand how the measure problem might affect the result in the simplified setting, where we just look at a single scalar field, and within a situation where we do have control, we can say this happens. Now, I agree that this may not be realistic, this may not be our universe, or this may not provide a solution of anything, but all we're saying is, let's look at this situation where we do have control. Let's look at how a particular solution to the measure problem that addresses the Young's paradox affects the solution, and this is what happens. It's